Hello, Chem 212 students, and welcome to our last lecture of this week about alkenes. The focus here will be a kind of summary of what we learned about the reactions, a short summary, and then applying this to synthesis. So synthesis is going to be a new type of problem that we're going to encounter in organic chemistry. Once we've had a few more reactions in our toolkit, we're actually going to have a whole chapter, chapter 11, just focused on synthesis. So let's start by reviewing what are the considerations when we're trying to predict the products of addition reactions. So we've gone through many addition reactions so far, quite a few. And now we want to pull it all together and say, how do we look at this reaction and predict what the products will be? What are the considerations when we're doing this? And then we're going to apply this to our synthesis strategies. So number one, when you're trying to predict the products of the addition reaction, you should analyze which reagents are being used. This will tell you what kind of addition reaction is happening. We've covered quite a few of them: hydrohalogenation, hydration, hydrogenation, halogenation, right, and so forth. And we had various kinds of hydrations that can, depending on the reagents, can affect the regioselectivity and the stereoselectivity of the reaction. So we want to think about what is the regioselectivity, Markovnikov or anti-Markovnikov. For example, when we're doing hydration, if we want the Markovnikov addition, we'll do the standard acid-catalyzed hydration. However, if we want the anti-Markovnikov regiochemistry, we're going to want to use the hydroboration oxidation. That's the one with the BH3THF, H2O2, NaOH as the second step there. Do you have to memorize these reagents? No. You're going to be given a list of these, which you can use on the exams. But you should start to begin to memorize them, because when you go into Chem 213, eventually this list will be taken from you. But for now, we're still learning. Okay, you're going to get a list for this whole class. After that, we want to determine the stereospecificity. Is this type of reaction a syn addition, where both of the parts of the reagent are added on the same side, or are they added on opposite sides? So this stereospecificity, we need to determine that. The more familiar you are with the mechanisms, the easier this will be. So I told you that you've got to memorize the mechanisms for the basic ones like the acid-catalyzed hydration, but also the more specific mechanisms like hydroboration oxidation, like oxymercuration demercuration, and also you need to know the mechanism for the halogenation, and that these go through the oxymercuration demercuration goes through the triangular shaped, which is something we've seen here, the triangular shaped intermediates, including, of which there were several. There was the mercurinium ion that we had that had the positive formal charge, and then it had the OAC on it, and this was across a double bond like that. And there was an analogous one with the bromine, which did a similar thing, had two lone pairs here, and it had a triangular shaped. And then we also had the epoxide intermediates. And so when this occurs here, especially, these kind of block one side for the subsequent SN to attack. So, oops, and there's the ether. I put it behind my head, but or the epoxide. But these will influence the stereochemistry. So you need to be aware of these mechanisms so that you're not straight memorizing products, right? You want to be able to understand why they are made, so that you don't have to memorize so much, because memory, it fails, but understanding lasts a long time. So once we understand all this, we know how to predict the products, we can use these to plan a synthesis. Synthesis means that you're starting with one reagent molecule, or sorry, one substrate molecule, and you're trying to produce a target molecule. So this is the way all of the unique molecules that are used, for example, in pharmaceutical drugs and in industrial applications, these are made by these synthesis plans. Someone sat down and figured out, how can I turn this molecule, what can I react with it to make it into the molecule that I want? So we started to talk about this for substitution and elimination in the end of chapter 7. But now we've got a whole bunch of new reactions we can apply that we've learned in chapter 8. And this reaction, which I call sometimes our toolkit, our reaction toolkit, is just going to keep growing through to the end of Chem 212 and into Chem 213. And so our options will increase and increase, and we'll need to use all of these reactions in our toolkit to help us to get from one reactant molecule to some product that we are interested in. So we have addition reactions, we have substitution reactions available to us right now, and we have elimination reactions. So let's say we want to change this molecule into this one. So clearly we can see a double bond. We're starting with a double bond. So this is telling us that we're in the end we don't have a double bond anymore. So this is telling us that we must have an addition reaction. In addition, we can see OH was added, and it was added at the more substituted position. So this is telling us we've got an addition, and it's a Markovnikov addition. And so we need to think, what kind of reagents could we use for this Markovnikov addition? And sometimes you'll have more than one option. There's always, there always can be multiple paths to get to the product you want, or a lot of the time. But here we need to add H and OH. So what can we use? Well, we can use the acid catalyzed hydration. We might be forced, if there was a concern about carbocation rearrangements, we might need to use the oxymercuration demercuration. However, because this OH is already added at the tertiary position, the intermediate is a tertiary carbocation here, and so we don't have to worry about rearrangement. So the acid catalyzed hydration would totally work here. And that's it. So this synthesis was one step. We were able to perform one reaction and get from our starting reagent to the molecule that we want. Most realistic syntheses have many, many steps. So we have to think about what would happen if we needed more than one step as well. But this is simple enough. We just put in the reagents that will take us here from our reactant molecule to the product molecule. Okay, here's another one, another kind of situation that you're going to see. So this was a one-step synthesis, simple enough. You're going to start to see certain patterns that will be a part of your synthesis reactions. One of those is taking a group and moving it to a different position. Okay, this can be regularly achieved by removing the group via elimination and then adding it back on via an addition. So in this case, we've taken off the bromine here by elimination, and then we put it back on. Okay, so this is going to involve two reactions, and so when you see one group moving and everything else staying the same, that's when you want to think of doing elimination followed by an addition. And so here, if we want to do this elimination here, eliminations, remember we have to treat with a base. All right, so we need some kind of base here to do this. And we want to avoid using a base that's also a very good nucleophile, probably, right? Because then we'll have a competition with substitution. So we want a base that's probably not a nucleophile. So what would be a good base here? Maybe like DBU or DBN, right? Like DBU, DBN, something like that. There are other options we'll see on the next slide here, but that's one possibility, right, for a reagent, DBU, DBN. Then we want to do an addition. And so this is going to be a hydrohalogenation. That's the Markovnikov addition. And so we could simply use the hydrohalide here to do this. And so here, here's breaking this down in steps. We could do this with a strong base nucleophile, strong base, strong nucleophile. We do want the Zaitsev product, the more substituted product. So we would use a non-sterically hindered base. And so that would be the advantage. So if we use DBU or DBN, that's a possibility, but it's a lot bigger molecule, right? So if we use the methoxide ion, it's smaller, it's not sterically hindered, so that would work as well. Although we'd had some worries about a little bit of substitution. but we would mostly get the Zaitsev product. So that's okay. So notice how we have two options here. I presented one with one that was a base and not a nucleophile. We could also use a methoxide, ethoxide, any of these strong base, strong nucleophiles. That would work too. We just have to worry about substitution. So here, the regiochemistry we want is the Zaitsev one, so that we can ultimately add the bromine at the more substituted position. If we use tert butoxide, for example, we'd end up with the Hofmann product, the less substituted product, and then we could only add bromine, in these positions here, but we want to add it over here. And so we use some base. Like I said, we could use DBU, DBN. We could also use methoxide here. Again, we'd have a little bit of competition with substitution, but we can separate these after, right? As long as there's not too much. We don't want a majority substitution product. So if you chose something that was, a bad base and a good nucleophile, well, that would not be good, because then you'd have preference for substitution rather than elimination. We follow it up with a hydrohalogenation. And so this is just one new tool that you have now that you didn't have before this chapter, because we did not have addition reactions yet. So you can do an elimination followed by an addition to move a group over. Here's another example where we have a reactant molecule that has an OH group, and our product has the OH group, but it's moved over by one spot. So again, this is another one where we want to do an elimination followed by an addition. And so we're going to do an elimination, and notice for the elimination, what we want is an elimination that can move us the OH group over here. So it's important that we don't do a elimination that produces the more substituted product. We don't want the Zaitsev product. We want the Hofmann product, the less substituted product. So here we're going to make sure to use a sterically hindered base to do this. And then we can do the addition of water, but notice again, we have to consider the regiochemistry. We want the OH group to be at the less substituted position. So we're going to want to do an anti-Markovnikov addition. So we should choose the appropriate reagents for that. So for the elimination, we want a sterically hindered base, so we could use tert butoxide. T-bu-OK is the way it's usually written, K being the potassium ion that's a spectator. And then we're going to want to do an anti-Markovnikov addition. So this is going to be our hydroboration oxidation. BH3, THF, to H2O2, NaOH. Okay, and so that's the strategy here. When you're moving over a group, do an elimination followed by an addition, but make sure that your elimination and addition will have the proper regiochemistry and stereochemistry to produce the product that you're trying to get. Now, one issue here is that that I did not mention is that the issue here is that when we do an elimination, we're going to have a kind of bad leaving group, right? OH is a bad leaving group, so this is not going to work directly. We have strategies for replacing the OH with a good leaving group, and that is to use the tosylates. And so, well, you might remember that we want to replace this here with a good leaving group. That leaving group would be OTS, and tosylate has this big bulky structure that I always give you. I gave it to you on the exam 2 sheet, just so that you remember that this TS represents a whole big group. So we would need to use tosyl chloride and a pyridine solvent first. This is going to be our general strategy here for replacing this bad leaving group OH with a good leaving group, the tosylate. And so the first step is to do the tosyl chloride and pyridine. That will replace the OH group with the tosylate, and then we can use the tert butoxide and do our anti-Markovnikov, our Hofmann product elimination here. So remember, that's one thing to keep in mind, is OH is generally a bad leaving group. There's two ways we can make it better. If we're reacting with an acid, we can protonate it, and then have it leave. However, when you're doing elimination, you want to do this in basic conditions. So the preferred method is to use the tosyl chloride and the pyridine and the tert butoxide. So this is going to be something you're going to start to see a lot when we're trying to get rid of the OH. And so now we have the elimination product. The next one we need to do is we need to do the anti-Markovnikov addition of OH, so we can put it down here on the edge. So let's see. So yeah, we want to do the anti-Markovnikov. We want the OH right here. So to do that, we're going to use the hydroboration oxidation. The acid catalyzed hydration. So notice we're not using here. We're not using the acid catalyzed hydration, H2O, H2SO4. We're not doing that because that would not give us the product that we're looking for. That would give us the OH attaching in the more substituted position. That would put it right back where it was before. And we don't want that. So we want the anti-Markovnikov addition. The oxymercuration, demercuration also wouldn't work because that would also produce the Markovnikov product, but we want the anti-Markovnikov product. Another move that you might see regularly is changing the position of a pi bond. So if we start with a molecule with a pi bond here and we want a pi bond over here instead, this is kind of the opposite of what we saw before. Here what we want to do is we want to do an addition to get rid of the pi bond, and then we want to do an elimination to reform the pi bond, but in another spot. So here, notice that when we do this addition, we need to make sure that it's anti-Markovnikov, because if we do a Markovnikov addition with HBr, that's going to put the Br in the more substituted position. Then when we do an elimination, we'll have the double bond in the wrong spot. So we need to start with an anti-Markovnikov addition of the bromine here. And then we'll follow that up with an elimination. And with the elimination, we want the Hofmann product. So we need to make sure to use a sterically hindered base. Fortunately, our leaving group, if we do an addition, let's say with bromine, our leaving group will be bromine. And so that will be a good leaving group. So we don't have to worry about, like we did with the last one with the OH leaving group, changing it to a better leaving group. Bromine's a fine leaving group. It can stabilize the negative charge great because it's large, right? Remember why. It's large and it has high electronegativity. So it stabilizes that negative charge pretty well. Okay. So in order to do the anti-Markovnikov addition, we cannot use HBr. HBr won't work. So no HBr, no HBr. We can't do that because that would put the bromine right here. But we don't want the bromine there. We want it at the anti-Markovnikov position. So to do the anti-Markovnikov addition, we use HBr, but we use it with ROR. So no HBr straight. It's HBr ROR, right? And this is a peroxide. And the peroxide has a special mechanism that we'll study when we study radical mechanisms in chapter 10, I believe it is. And then we will then produce the anti-Markovnikov. And I'll explain to you in chapter 10 when we talk about how to draw the arrows for radical mechanisms. I'll explain to you why this is at that time. So once we get to that chapter, for now just refer to your reaction list, but once we get to that chapter, I'll teach you the why behind it and you won't have to be memorizing it. And then we want the elimination, and so for this elimination, we want to use a bulky base to get the Hofmann product. Now again, of course, there's going to be a little bit of competition with substitution, right? So we'll also get a little bit of the substitution product, but the major product will be the elimination product because this substrate is secondary, so we're fine there. We don't have to worry too much. And so that's how we would do this. So here's a summary of all the reactions that are covered in this chapter. The hydrohalogenation, which produces the Markovnikov, so this would be like the HBr, for example. The hydrohalogenation anti-Markovnikov, this is like the HBr, but with ROR, or HX with ROR. HCl or HBr would work. Br works better. Acid catalyzed hydration, oxymercuration, demercuration. So those are both going to be these ones. These ones will both give you the Zaitsev. Oh, sorry, the Zaitsev. Sorry, Markovnikov product. I keep reversing those. Markov, I'll just say Markovnikov product. This is going to give you the anti-Markovnikov product. Do you need to know these guys' names? No. Like Hoffman, Zaitsev? No. Markovnikov. Just as long as you know that that we can have Markovnikov, which is the more substituted edition, or versus the anti-Markovnikov, which is a less substituted edition. We have hydrogenation, which generally, if you just use H2, that occurs in the syn fashion. We have the bromination, halogenation here. So this is anti, this one's syn. Because, and remember, if you understand the mechanism, you'll know why. The hydrogenation, at least the metal catalyzed one, occurs on the surface of the metal, and so the addition of the hydrogen happens on the same side. Whereas with bromination, we go through the bromonium intermediate, which, as a result, the nucleophile must attack from the backside. And my arrow's a little bad here. It should be pointing to one of the carbons. But yeah, so oops, there. So yeah, when the subsequent addition of the other bromine occurs, like this, Br, it's going to have to attack from the backside, like an SN2, and then this will open up. And so that's why you end up with an anti-addition. The halohydrin formation, this is what happens when you use something like HBr. There's water present, right? Anti-dihydroxylation versus syn-dihydroxylation, and finally ozonolysis. So we have added 10 reactions to our reaction toolkit, a large number. So there's lots that we can do in terms of synthesis, and there's lots to do in terms of practicing predicting the correct products with the correct regio and stereochemistry. So here's a summary of all those reactions. Let's just briefly go through them to review in the order that we did them. So we have the hydrohalogenation, which notice that in this double bond, the halogen gets added to the more substituted position, right? The Markovnikov, as it's called. If we want to do an anti-Markovnikov, we have to add a peroxide in here. And that will notice the difference here. We can put the halogen atom at the less substituted position. We can also have a Markovnikov addition of water, where the OH group goes in the more substituted position. You can use acid catalyzed hydration to do that. Or you can, if you're concerned with carbocation rearrangements happening, that's not a concern on this one, but it could be on other molecules, you will instead use the oxymercuration demercuration, where you use the mercuric acetate with water and then follow up with sodium borohydride treatment. If you want to add the hydroxyl in the anti-Markovnikov position, well, then you're going to have to use hydroboration oxidation here. And remember that because of the way this works, you're going to have the addition of the H, which isn't shown, but this H here that's added is going to be on the same side. This is a syn addition, and because of the way the mechanism works. And this is a complex mechanism. You do need to know the mechanisms for all of these so far, okay? So from 1 to 4, you need to know the mechanisms. And that's all of these right here. You need to know the mechanisms for these. For the addition of H2, remember that this is also going to be a syn addition. But the mechanism here is just, it's shown, it was shown basically with a picture. You have the hydrogens attached to a metal surface, and then they add to the double bond. I won't ask you to draw a 3D picture of metal surfaces, so you don't have to worry about a mechanism for this one. For this one, you do need to know mechanism right here, and for the halohydrin as well. So these two right here, 6 and 7, you need to know the mechanism for these. You don't need to know it for, and I'll just put, whoops, you don't need to know the mechanism, or at least you won't need to draw the mechanism for this one. So you don't need to know the mechanism for this one. You don't need to be able to draw the mechanism. You should understand why it's anti here. You don't need to draw the mechanism for this one, and there's no mechanism for that one. So you need to know the mechanisms through 1 through 4 and 6 and 7. Remember, this happens in a syn fashion, whereas the halogenation here, the bromination, happens in an anti fashion. This is anti. Okay, anti. And this is because it goes through the bromonium ion intermediate. That's why it's really important to know the mechanism for this one. We also have the halohydrin formation when you have the halogen with water as the solvent. And so here you're going to get, again, an anti addition. This is going to be anti addition. So the bromine and the OH group will be added on the opposite. The OH group goes in the more substituted position. And this is, knowing all of this, knowing the regiochemistry and the stereochemistry, this can all be known as long as you understand the mechanism. You don't need to memorize all this information as long as you know the mechanisms, right? If you use a peroxy radical and an acid, you can get a dihydroxylation. This is the anti-dihydroxylation, here. And if you use KMNO4 with NaOH or use OSO4 with sodium bisulfite, you get the syn addition. So this one's syn of 2 OH groups. You get the syn addition of 2 OH groups. Both of these, syn. And finally, we have the ozonolysis, which just means you break this double bond, you break it right here, and then you put an O there and an O there, double bond to an O, and so that you get that. And in this case, it broke open the ring, right? But we have an O on this second carbon, so if this is carbon 1 here, and this is carbon 2, this is carbon 1, this is carbon 2. So we have the carbon double bond oxygen to carbon number 2, and then we have 3, 4, 5, 6, and we'll call this one 7. And these are just, I'm just numbering them so you know what they are. So this will be 2, 3, 4, 5, 6, and 7. So on the 7th carbon here, we have a carbon double bond to oxygen. So make sure to count your carbons with these ozonolysis. It's easy to forget one. And make sure that your carbon double bond oxygen goes on the correct carbon. And that is a summary of all the reactions we've learned. And I've assigned a few problems where you can practice with the homework on synthesis, but as we move forward, we're going to have a whole chapter on synthesis, and on the next exam, we will have synthesis problems. It will be the beginning of having synthesis problems on the exam, and on the final, there will be quite a number of synthesis problems, and so this is now the time to start practicing with the homework. So I want to wish you the best of luck on the homework. Please let me know if you have any questions. I want to help you. And I hope you have a great week. I'll see you in next week's videos.